first speaker this afternoon is Sasha Sherstov, who will tell us about algorithmic polynomials.
The key notion in this work is that of epsilon approximate degree. So let's fix an arbitrary function. It could be a real function, a Boolean function. The epsilon approximate degree of f is the minimum degree of a real polynomial that approximates f pointwise within epsilon. So this notion is very natural. It was defined a long time ago in 1992 by Nissan and Segedi in their pioneering work, where they proved in particular that a polynomial of degree root n is sufficient and necessary to approximate the OR function. So throughout this talk, I'll use this shorthand notation for epsilon approximate degree. Since its introduction, this notion has found a variety of applications. Both the lower bounds and upper bounds are of interest. The lower bounds typically give you impossibility results and hardness results for other models, such as circuit complexity, quantum query complexity, communication complexity. And there's been a lot of progress along those lines, using approximate degree as a vehicle to solve hard open problems. Upper bounds on approximate degree are also of interest. They typically give you algorithms, such as learning theoretic applications, more generally applications to algorithm design, and other applications as well, such as differential privacy. Sometimes upper bounds also give you lower bounds, as was shown by Avishai in his work on and/or formulas. Okay, a watershed moment for this quantity came with the publication of this work in '98 by Beals, Berman, Cleve, Mosca, and DeWolf. So they made the following simple but absolutely crucial pivotal observation. A quantum query algorithm for a function with t queries automatically gives you an approximating polynomial for the same function of degree 2t. So having a quantum algorithm for a function gives you automatically a polynomial approximating that function that has the same complexity. And since then, virtually all known upper bounds on approximate degree have come from quantum algorithms. So this is both good and bad. Certainly the community has benefited immensely from the quantum method, but there are problems to limiting our toolbox to the quantum techniques. So why is that problematic? First of all, quantum polynomials typically are not constructive. You can sometimes derive the approximating polynomial from the algorithm if you try hard enough, but in some cases, or I should say in most cases, of non-trivial complexity, such as the element distinctness function, the polynomial that you recover in this fashion is so complex that it's as good as no polynomial at all. So they're non-constructive. They're typically more complicated than a construction from first principles. And finally, and this is the most important point, there are examples where they're less efficient than polynomials. So the first point you can sort of live with. The second point is perhaps more of a big deal. But the third point is really a deal breaker. In this talk, we're going to look at a number of breakthrough quantum query algorithms. And in each case, we're going to design a first principles approximating polynomial for the same function with the proof fitting on half a page or on one page. In all cases, we're going to match.
What font is that proof?
Okay. Well, so I'll take advantage of some modularity, and there'll be some common components to the proofs, which I'll factor out, and then that won't count toward the length of the individual proofs. But when you see the proofs, hopefully you'll agree that they are dramatically simpler, and they're first principles. The only preliminary to following this presentation is the Chebyshev polynomial. Nothing else. Okay, and performance-wise, we're going to match, quantum, or improve it polynomially. So in particular, as our main theorem, we're going to exhibit the first natural problem with a polynomial gap between approximate degree and quantum query complexity. Okay, so let's get started. As a warm-up, we'll look at symmetric functions. So let f be an arbitrary symmetric function, and let's say that it is constant on inputs of Hamming weight between k and n minus k. So this is just in the nature of things. This turns out to be the right characterization for symmetric functions. Then its epsilon approximate degree is given by this expression. You might wonder why we even care about all epsilon as opposed to a small constant epsilon, as is usually the case. Well, symmetric functions are used as a building block in most constructions involving approximation by polynomials. So much so that you actually need tight approximating polynomials for the symmetric functions for all ranges of epsilon. And you'll see that later in this talk as well. Okay, so this gives you a complete characterization of the epsilon approximate degree. Prior to this work, the theorem was known only, so the theorem was known, but the only proof was due to Ronald DeWolf from 2008. And the proof that you'll see is an explicit and first principles proof. So actually the paper has 3 proofs for this theorem, but you'll see one of them. There's a combinatorial proof and 2 approximation theoretic proofs that have nothing to do with each other. Yeah.
The assumption in the theorem is symmetric in around n over 2, but the lower bound is not. I mean, the upper bound is not.
So a very good point. Yeah. So actually, you don't need the symmetry assumption for the upper bound. In fact, the theorem holds for all functions that vanish in this range.
That's not what I asked.
What was your question?
I talked about the symmetry in where it is constant. It's symmetric about n over 2. It's between k and n minus k.
Yeah, but k is at most n over 2.
Yeah.
Right, k is at most n over 2.
Yeah, k is at most, but you have n times k. Okay. K
Yeah,
is at most. You say k is not. Yeah.
Right, right. So this turns out to be the right expression.
Yeah.
Okay, so this is just to get us started. The next function we'll look at is element distinctness. That really is the key one, perhaps the most studied problem in quantum query complexity, other than search. So there's been a lot of work on this problem. The problem is, given n integers from a range of size r, determine whether the integers are pairwise distinct. So typically, traditionally, the input is represented by a matrix of size n by r. So the n rows correspond to the n elements, and the n columns correspond to the possible values that each element can take. So in the ith row, you put a 1 in the jth column if the value of the ith element is the jth value of the universe. Okay, so the input matrices have exactly 1, 1 in each row. And so we'll consider a more general setup where you're given an arbitrary Boolean matrix of order n by r with at most n ones. We don't care how they're placed within the matrix. It really doesn't matter. And then the function is defined by 1 if there's a row with if there's no row with a repeated entry and 0 otherwise. So you can consider a generalization of this problem to k distinctness, where the parameter k is set to 2 in the version that I just described. In general, you're looking for a k-tuple of repeated elements. And here, the answer that we obtain is this. So it looks somewhat strange when you see it for the first time. But magically, it's precisely the quantity that Belovs obtains in his quantum algorithm that uses a completely different technique. So Belovs' proof is arguably one of the most advanced proofs in quantum query complexity. And it's based on this beautiful, powerful framework of learning graphs. So he gets the exact same answer using a completely different set of tools. So this gives me hope that this is actually in the nature of things. So this is the true answer. But as of today, it's open.
Sorry, you mean even in terms of k and the constant as well, or there are some?
So the problem is parameterized by this constant k, and all other parameters can be arbitrary. So the constant within the big O notation depends on k alone.
But I'm asking regarding the tightness. So you mean that 1/2 minus 1 over 4, 1 minus 2 to the, is this tight? You think that constants are tight as well?
So I strongly believe that it is, but this is only known to be true for k equals 2. Right. It's a difficult problem. Okay, and the last result that we'll look at is k-DNFs. This is perhaps the most flexible or general class of functions in quantum query complexity. Here you can handle arbitrary properties that have k-certificate complexity or one certificate complexity or 0 certificate complexity at most k. So here the bound that we obtain is this. The variables that are inputs to your k-DNF or k-CNF could be, there could be infinitely many of them. So this is an important point. This result holds for the setting where the function has as its input bits arbitrarily many variables. The only restriction that you make use of is that the Hamming weight of the inputs could be at most n. So under that promise, the bound holds. So this reproves and generalizes the best previous quantum lower bound due to Ambinus, who used, again, a sophisticated algorithm based on a random walk, a quantum walk on the Johnson graph. Okay, up to this point, every single result I've talked about has been a new proof of something that we already knew from quantum techniques. Which brings me to the final slide of the results overview. Okay, the surjectivity function. The surjectivity function is similar to the element distinctness function. Again, you're given n elements from a range of size r, and you're asked whether the entire range is covered. So the input is exactly the same, it's formatted exactly the same, but what you need to compute is different. Okay, so this is the formulaic description of the function. In a beautiful result, Paul and his student Vilat Machmuchi proved that this problem has linear approximate degree, linear quantum query complexity. So they exhibited the first problem in AC0 that has maximal quantum query complexity. And this was a very comforting piece of news. It was conjectured, agreed upon, I should say, or hypothesized by all experts that this is also the right answer for approximate degree, which would have a variety of other applications. So that would be a terrific state of affairs if that were true. But as it is, surjectivity decided otherwise, and it turned out that it does not have linear approximate degree. So we disproved this conjecture that the approximate degree of this function is n, and in reality, it turns out to be n to the 3/4 at the most. Okay, when you compare the linear complexity for algorithms versus the complexity of n to the 3/4 for polynomials, you get a polynomial gap between the two quantities. So polynomials outperform quantum algorithms.
What is the largest gap possible?
Good question. I think it's a power of 2 or power of 5 halves, some such thing. So this isn't the largest, quantitatively this isn't the largest gap. So in his original work, Andrus Ambinus exhibited a specially constructed function that has a gap between approximate degree and polynomial degree. When I say that this is the first natural function, by that I mean that the function has been studied on its own merits and is of interest in its own right, and was not explicitly constructed with the purpose of separating the two complexity measures. Okay, so this completes the results overview, and now I'll jump into the technical part of the talk. As promised, the only preliminary that you need for the proofs is knowledge of the Chebyshev polynomial, which is this family of polynomials. They're extremal in a very precise sense. They're a staple in approximation theory. They're bounded on the unit interval by 1 in absolute value, and they exhibit extremal growth beyond the unit interval at every point. Okay. So given this only tool as our starting point, we develop two higher-order preliminaries, higher-order primitives, I should say, that are of interest, I think, well outside the scope of this work. The first is a very natural approximation theoretic problem. I call it the extension problem. So here you're given a function defined on inputs of Hamming weight up to m. And you would like, and you have an approximate for f for inputs of Hamming weight up to m. Now you're considering an extension of f to inputs of Hamming weight n. An extension defined naturally by setting the function's output to be 0 on the new inputs. So approximation theoretically, you'd like to know whether an approximant for little f can be converted somehow in a black box manner to an approximant for big F. So it would be terrific if that were true. Unfortunately, that turns out to be impossible. If you think about it for a few minutes, you realize that there's a simple counterexample. But morally speaking, the statement is true. What you can do is you can start with an approximant for the extension of f to inputs of length 2m. And from then on, once you have the approximant for that initial extension, extending it further beyond 2m is very inexpensive. So this is the theorem that we prove. Once you have an approximant for the extension of f to inputs of Hamming weight 2m, extending it any further is extremely efficient. So you're paying a multiplicative cost of n over m, the square root of that. And there's this additive error term. And the theorem is tight with respect to all parameters. Okay, so a general purpose primitive that will be used in, I think, all of the proofs. Okay, the other primitive concerns functions that can be expressed as Boolean inner product, if you will. So it's a function of this form where you have x1 ANDed with fi. And each fi is a function on some universe. Okay, so the x and the y parts are tightly coupled, and we could hope to understand the approximate degree of any disjunction of the f's. In our applications, the f's will be DNFs. So you're going from a k DNF to a k-1 DNF to a k-2 DNF. This is the case in all these settings, like k-element distinctness. And we can also hope to understand the x part separately, but they're coupled here. So the contribution of the decoupling theorem is to decouple the x part and the y part. So for any b, we prove this upper bound on the approximate degree. So you're approximating the x part separately, you're approximating the y part separately. So here you're approximating disjunctions of the f's. And here you're approximating disjunctions of the x's. And then you're able to merge the results. So this holds for every b. And if you optimize over b carefully, as we do in applications of the statement, you get tight bounds. Okay, so these are the preliminaries. Now let's see the proofs, and hopefully I can justify the comment I made earlier to Rocco that they fit on half a page. All right, let's start with the easiest proof. So you're given a symmetric function that is constant on inputs of Hamming weight between k and n minus k. And then its approximate degree with the error parameter set to epsilon is that. So without loss of generality, let's consider it bounded. Let's examine a one-sided version of this theorem. I mean, once we have the one-sided version, and then we have the function that's zero on zero everywhere except for inputs of Hamming weight at least n, at most n, n minus k, so we just merge them. Anyway, so the theorem we'll look at is you're given a function that is constant on inputs of Hamming weight greater than k. And this is the bound that we want to prove. We will not use the symmetry assumption at all. So how does the proof work? Well, you consider the function, and you extend it to inputs of Hamming weight k plus log 1 over epsilon. And since the function is 0 everywhere above the kth level of the hypercube, you can extend it further to inputs of this Hamming weight. That'll be a legitimate extension of the original function. What you're really interested in is the extension of the original function to inputs of Hamming weight n. So here's the proof. It's one line, in fact. This is the original function, right? You are going to compute it to 0 error on inputs of Hamming weight at most 2 k plus log 1 over epsilon. Once you have this initial function, you're going to extend it. Well, this is your starting point, the blue shaded area here. And then once you have that, you're going to extend it to the entire domain. You're paying an additive term of log 1 over epsilon, and this is the multiplicative term. So,
but what is this number?
What is this number? So here we're just going to use straight interpolation. So the most inefficient, the most brute force approach. Just at most, I mean, you can compute any function on inputs of Hamming weight at most k by a polynomial of degree k, just by straight interpolating it.
So this is using symmetry then, right?
No. So you don't need any. So it's straight interpolation. Not hiding anything
So
there.
you're not bounded outside, like the function f2k plus something that is not bounded outside of the from.
The polynomial does not need to be. That's the extension problem. Is that you only deal with it on inputs of length of Hamming weight up to something, and then beyond that you're just going to extend effortlessly. So you don't have, a priori, you have no control over the approximate on those inputs to which you try to extend. Yeah. Okay, in the paper there are two more proofs, one of which is combinatorial. Okay, now let's look at surjectivity, where we get the separation of quantum algorithms from polynomials. So here the theorem that we prove is if your range has size r, then we can show a sharper bound. In all cases, we prove a bound of size n to the 3/4. Okay, let's see how this works. Let's just write the function down as it is defined. And the outside gate, the outer gate, we're going to approximate by Chebyshev. So then we have this expression. All I've done here is approximate the AND gate by Chebyshev polynomial. And you know everything about Chebyshev polynomials that you could ever ask. So if you multiply this out, you get a linear combination of these. Well, let's first flip them so that they're monomials. So I'm going to use De Morgan's law to switch them to monomials. And now I'm going to multiply this out. Now the coefficients of the Chebyshev polynomial are bounded by 2 to the degree of the Chebyshev polynomial. So when you multiply out, you get a linear combination of terms where the sum of the coefficients is bounded. And once you have that, You take the terms one by one, you rip the term out, you replace it by an approximating polynomial with error inversely related to this quantity. And then you plug that back into the sum. So this really shows the power of polynomials versus quantum algorithms, because you can't do that kind of surgery on a quantum polynomial. You can't hope to consider the approximating polynomial and rip out an individual term and replace it by something completely different. You just don't have control at that physical level of the approximating object. And perhaps this is also a good place to explain the title of this talk, Algorithmic Polynomials. The informal message of this work is that if we need polynomials, as we do for learning applications or applications to differential privacy, complexity theoretic applications sometimes, we do not care where the polynomial comes from. So we should construct them from first principles. And the approach of this work is to use approximation theory, traditional approximation theory, which is used to prove these extension theorem and decoupling theorem, along with basic principles of algorithm design, such as divide and conquer, sampling arguments, inclusion, exclusion. So the approach of this work is aptly called algorithmic polynomials, because the focus is on polynomials as opposed to algorithms. Okay, now let's look at the harder two theorems, the hardest two theorems of this work. Here we'll look at KDNF formulas, and this is the bound that we are aiming for. Again, the formula has as its inputs big N variables. The formula is a KDNF, and your bound should not have a dependence on big N. It should only depend on the maximum Hamming weight of the inputs in your domain. So let's fix some notation. Let d of n k epsilon be the maximum approximate degree, maximum epsilon approximate degree over k DNFs on an arbitrary domain where the Hamming weight is bounded by lit n. The number of variables is infinity. Then from first principles, by interpolation, we get this bound. And then using the decoupling theorem, you get this alternate bound. So how is this exactly applied? Well, a KDNF is a k-1 DNF, a sequence of k-1 DNFs, coupled with individual bits by definition. So you approximate the individual bits, or rather disjunctions of individual bits separately. You approximate the k-1 DNFs separately, and then you get this expression. There's a slight technicality there where you have to deal with negations, but that can be taken care of. Okay, so when you solve this recurrence, you get this expression, which is the claimed, here it should be k plus 1, which is the claimed upper bound. Okay, and the last result I'll sketch for you is element distinctness. Here, you're given an arbitrary matrix of size n by r, and you'd like to figure out if some row has greater than k entries of 1. So this is the bound that we are aiming for. Again, we're going to define this parameterized quantity d of n, r, k, and epsilon. So it's the maximum of all functions that can be expressed as the disjunction of r parts. Each part is a threshold predicate with the threshold parameter set to k, and the threshold predicates are applied to disjoint sets of variables. So this is a generalization of element distinctness. And the size of the underlying universe can be unbounded. So here the proof is slightly more delicate. Again, you start with a bound that uses just interpolation, straight interpolation. That is the base case of your inductive argument. Then you use the extension theorem and the decoupling theorem to come up with two complementary upper bounds for the inductive step. The first bound is useful when the number of parts is small. So the number of values is small and you're looking for a k repetition of some value. So this uses the extension theorem alone. Here, you assume that you have infinitely many parts. So the number of range items could be infinite. And the number of elements is at most n. And you have this complementary bound. When you combine them and solve the recurrence, you get this answer, which is what I promised on the first slide. Okay, so now let me get to the open problems. The most compelling open problem that arises naturally from this work is whether every function in depth 2 AC0 has approximate degree bounded away from n. So approximate degree of n to the 1 minus epsilon d for some positive epsilon sub d. So prior to this work, the consensus was that this definitely is not the case, and surjectivity, in fact, is just such a function that should have linear approximate degree. But at this point, there is no reason to believe that this is ruled out. There are some candidates, such as approximate majority, but their status is highly uncertain. And I would be, so I think both directions, both outcomes are equally likely. Okay, this is a workshop on lower bounds, so let's have 3 problems that have to do with lower bounds. They are the natural ones. Show that the upper bounds in this work are tight. And as of today, this is only known for surjectivity. This was solved in a beautiful paper by Bunn, Kotari, and Thaler. So Mark is going to talk about that work next. So that paper uses the sublinear upper bound on surjectivity as inspiration to prove lower bounds on a number of other problems. The status of the other 2 problems remains wide open. They're difficult problems, both KDNF and K-element distinctness. They've seen a lot of work. Yeah, both of these problems have seen a lot of work, and it's not clear quite how to proceed. Okay, one other exciting bit of progress that I should mention is there's a paper by Mark, Justin, and Robin that was posted, I think, literally a few days ago on ACCC. That makes progress on the first point. So the authors use the technique in the surjectivity proof that I just showed you iteratively, right? So surjectivity is depth 2. If you have a circuit of depth d and you apply the same technique iteratively, then you get an upper bound of maybe not n to the 3/4, but something that is still sublinear. So if your circuit has a number of gates that's bounded by n, then the hypothesis is true. So these authors prove that the answer is yes if your circuit has linear size. But in general, the status of this question remains wide open. Yeah, so all three problems here are quite, I think, very fundamental and very challenging. So they're fun problems to work on. Thank you.
Maybe while Mark sets up, we can take a question if there is one. Questions?
What about proving, the results at any formula is an approximate degree of square root s? That's for the formula size. How about proving this?
That's a great question. Right. So that's another powerful result proved breakthrough result, I should say, proved using quantum techniques, and no classical proof is known. Great question.
It's a special case of if given the NAND tree.
Right.
I mean, you don't know for classical.
Yeah, it would be great to have a classical proof for that as well, because the result is of interest well outside of quantum query complexity.